Welcome everyone to the 16th lecture of the course Discrete-time Markov chains and Poisson processes. So, I am Subhamay Saha and I will be teaching the remaining part of the course. So, previously you were being taught by Dr. Ayan Ganguly. So, before starting, just let me make a quick recap of what you have learned till now. So, you have seen the definition of discrete-time Markov chains, you have seen what is its transition probability matrix, and you have also seen that the evolution of a discrete-time Markov chain is completely specified by its initial distribution and the transition probability matrix. Then you saw the concept of communication. So, what is meant by two states communicating. So, I and j are said to communicate if you can go from I to j in finite number of steps, and you can also go from j to I in finite number of steps. If this is true, you say I and j are communicating, and all states which are communicating among themselves, they form a communicating class, and if the Markov chain has a single communicating class, then you say that the Markov chain is irreducible. Fine. Then you saw this classification of states, namely transience and recurrence. So, a state I is said to be recurrent if starting from I you come back to I in finite time with probability 1, and it is said to be transient if there is a positive probability that starting from I you never come back to I. So, that was transience and recurrence. Then you saw a few equivalent characteristics, like how to prove whether a state is recurrent or transient. One important result was that every recurrent class is closed. That means, if you start from that class, you will remain in that class forever. And when it is a finite state Markov chain, it becomes an if and only statement. That means, a class is closed if and only if it is recurrent. But today we will see that this statement is not if and only if it is an infinite state Markov chain. So, one way it is always true that if it is recurrent, then it is closed, but if it is finite state Markov chain, then closed implies recurrent. But today we will see that if it is an infinite state Markov chain, then closed may not imply that it is recurrent. Fine. Okay. So, let us look at that example. So, again recall the definition of a simple random walk. So, what is a simple random walk? So, you basically start from 0 and then you at every step you go to either right or left. So, you go right with probability p and you go left with probability q. Fine. So, you start from 0 and then either you will go right with probability p or you go left with probability q. Say suppose you go right, then you are at 1, then again from 1 you will either go right with probability p or left with probability q. So, that is a simple random walk where this p plus q is equal to 1 and p is assumed to be strictly between 0 and 1. Fine. Now, it is very easy to see that this is irreducible, right, because you can go from any state to any state. It is easily seen from the transition diagram, right. So, you like for example, you take any step, any two states I and j, you can go from I to j, right. For example, if j is to the right of I, you just make moves to the right and you reach j, fine. So, again it is very simple to see that any two states in a simple random walk communicate. So, it has a single communicating class, or in other words this Markov chain is irreducible, fine. So, basically now we want to check what these like the states are recurrent or transient. Now, since you have already seen that this is irreducible. So, and since this transience, recurrence are all class properties. So, if I can show that one state is recurrent, then all states are recurrent, and similarly if I can show that one state is transient, then all states are transient, fine. So, let us examine the state 0, fine. So, now starting from 0, you can return to 0 only in even number of steps. Why is that? That is because, like see, starting from 0, if you have to return to 0, then you will have to make equal number of right moves as well as equal number of right and left moves. The number of times you go right, the same number of times you have to go left, or in other words, the number of times you go left, you have to make same number of right moves, right. So, starting from 0, like for example, let us see. So, if you start from 0, say in first step you go here, then you go here. Now, if you have to return, then so you have made 2 right moves. Now, if you have to return to 0, you will have to make 2 left moves. So, starting from 0, if you have to return to 0, then that in that path there should be equal number of right moves and as well as left moves. So, number of right moves and left moves should be equal. That means the number of steps should be even, because the number of right steps should be equal to the number of left steps. Only then, starting from 0, you can return to 0. So, starting from 0, you can return to 0 only in even number of steps, fine. Thus, you have that P00 to n minus 1 equal to 0. So, starting from 0, you cannot return to 0 in odd number of steps. So, for n greater than or equal to 1, 2n minus 1 are all odd numbers. So, you cannot start. So, P00 to n minus 1 is the probability that starting from 0, you are at 0 in 2n minus 1 steps. But since you starting from 0, you can be in 0 only after even number of steps. So, P00 to n minus 1 is equal to 0. Now, P00 to n is 2n choose n p to the power n times q to the power n. Now, let me explain why this is true. Fine. So, as I said, now say suppose you start from 0. Now, if you have, so you go right, say again you go left, again you go right, again you, so and you return, right. So, the main thing is the number of right steps should be equal to the number of left steps. So, if you have a path which starts from 0 and at 2nth step, so the path certainly has to be of even length. So, we take 2n. So, if you have a path of length 2n which starts from 0 and at the 2nth step you are at 0, that means in that path the number of right steps is n and number of left steps is also n, because the number of left steps should be equal to the number of right steps. So, if starting from 0 in 2nth step you are again at 0, that means in that path there are n right steps and n left steps. So, now we want to count how many such paths of length 2n is possible. But how will you count that? For that you basically just need to choose in which steps you made a right move, right. Among 2n steps, in n steps you will have to make a right move and in n steps you will have to make a left move. But if you just choose the steps in which you make a right move, then in the remaining steps you make a left move, right. So, now from 2n steps you need to just choose n steps in which you make a right move. How do you do that? How do you choose n objects from 2n objects? That is precisely 2n choose n, fine. Now, in that there are n right steps and n left steps, right. Left step you make with a probability p, and so there are n, so it is p to the power n. Remember, all these are independent. So, n right steps probability is p to the n, and there are also n left steps whose probability is q to the n. So, this gives you the probability that you starting from 0 in the 2nth step you are at 0. So, this 2n choose n is basically the number of such paths which starts from 0 and is at 0 in the 2nth step, and then this is this p to the power n and q to the power n is basically the probability of each such path. So, the total probability is given by this, fine. So, that is why P00 to n is this 2n choose n p to the power n times q to the power n, and again this is true for all n greater than or equal to 1. So, p002 n minus 1 is equal to 0 and p002 n is equal to 2n choose n times p to the power n into times q to the power n. Fine. Now, in order to proceed further, we will need a fact which is called Starlings formula, which tells you what is n factorial. Like it gives you an approximation or an asymptotic of n factorial. It says that n factorial is like square root 2 pi n to the power n plus half times e to the power minus n, right. Now, as n goes to infinity. Now, you do not have to actually know, like, let me not go into the detail of what this tilde means, but what this, like, only thing you need to understand here is, if in a calculation you have n factorial, then you can replace it by this quantity which is square root 2 pi n to the n plus half e to the power minus n. So, if you do that, the result you get is correct. That is what Starlings formula tells you roughly. I do not want to get into the like what this tilde actually means mathematically, let me not get into that, but for the purpose of this example, what you will need is you can replace n factorial by square root 2 pi n to the power n plus half times e to the power minus n. Fine. Okay. Now, using this Starlings formula, we already know that p002n is 2n choose n times p to the n times q to the n, but 2n choose n is precisely. So, remember what is 2n choose n? What is 2n choose n? It is 2n factorial divided by n factorial times n factorial. So, you get 2n factorial divided by n factorial square times p to the n times q to the power n. Now, I will use this Starlings formula. So, this calculation again it is a pretty simple calculation. So, you have to just replace. So, n factorial you replace by that, and 2n factorial also you use Starlings formula. So, once you just replace that, what you will get, and you do that calculation, I am not doing the calculation here, but it is a very simple calculation. So, that will give you that p002n is this. Fine. So, what have I done here? I have just replaced n factorial by that Starlings formula. Remember this, you have 2n factorial. So, basically if you are going back to this, so here this is the approximation for n factorial. So, if you have to do 2n factorial, so instead of n you will have to take 2n, fine, in the calculation here. So, when you do the approximation for 2n factorial, instead of n you just put 2n, fine, and in the denominator is just n factorial, fine. So, what I have done here is I have used Starlings formula to replace n factorial, and then I get this quantity, fine. Okay. Now, there can be two cases. Case 1 where p is equal to q equal to half. This is what is called the simple symmetric random walk, fine. Now, if p equal to q equal to half, then obviously 4 times pq is equal to 1. Now, then n running from 1 to infinity, p00 n is equal to summation n running from 1 to infinity p00 to n, that is because the odd terms are all 0. So, you get only sum over the even terms, but now this p00 to n is given by this quantity. So, what I get is this, but now we are using this fact from analysis that summation 1 over square root n is equal to infinity. This is a very basic fact from calculus, that if you take this series n running from 1 to n, summation n running from 1 to n 1 over square root n, then that is equal to infinity, fine. So, you have got that n running from 1 to infinity p00 n equal to infinity, and we have already seen that is precisely say. So, if that is true, then 0 is recurrent, because you have already seen this, that a state I is recurrent if and only if summation I running from 1 to n p(i)(i)n equal to infinity, and if it is finite, then it is transient. So, here what we have shown is that summation I running from 1 to n P00n is equal to infinity, so 0 is recurrent. But since we have already seen that this Markov chain is irreducible, so and transience, recurrence are all class properties, so every state in a simple symmetric random walk is recurrent. Fine. So if P equal to Q equal to halves, or in other words, if we are looking at a simple symmetric random walk, then all the states are recurrent. Fine. Okay. Now we look at the case P not equal to Q. In that case, 4PQ is strictly less than 1. So this you can easily check that when P is not equal to Q, 4PQ is strictly less than 1. Therefore, now again we look at the same summation, n running from 1 to infinity P00n is equal to n running from 1 to infinity P002n. That is again because the odd terms are 0, because you cannot return starting from 0, you cannot be at 0 in after odd number of steps. Now again we are using this, we know that P002n is given by this. So 1 over square root pi n running from 1 to infinity 4pq to the power n by square root n. But now 4pq is, this is some quantity, say you can call say 4pq is equal to say some r, 4pq is equal to some r, but the important thing is r is less than 1. Fine, the important thing is r is less than 1, so you get this summation. But now from the denominator, if I see square root n is always greater than or equal to 1. So if I replace square root n by 1 in the denominator, this will be less than or equal to this, because I am making the denominator small. So the term becomes large. So this sum is less than or equal to this sum. That is because square root n is greater than or equal to 1 for all n greater than or equal to 1. But now this 4pq, as I said, think of it as some r, which is a quantity strictly less than 1. So this is nothing but a geometric series, right? So n running from 1 to infinity, some r to the power n, where r is strictly less than 1. This is a geometric series, and you know that this is finite. So n running from 1 to infinity P00n is less than infinity. Thus in the asymmetric case, so if P is not equal to Q, in that case P0 summation n running from 1 to infinity P00n is less than infinity, and hence 0 is transient. Again, since the Markov chain is irreducible, so 0 is transient tells you every state is transient. So an asymmetric simple random walk is in an transient. So we saw that as a simple symmetric random walk is recurrent, but an asymmetric simple random walk is transient. Fine. So when P is not equal to Q, the asymmetric simple random walk is transient. But now remember I said that today we are going to see an example which will show that in the infinite setting it is not true that closed implies recurrent. In finite setting it is true that closed implies recurrent. Recurrent implies closed in both the situations, but like recurrent implies closed in whether it is a finite Markov chain or it is an infinite Markov chain. But when it is a finite Markov chain, it is an if and only if statement, that recurrent if and only if closed. But this example of asymmetric simple random walk shows you that in infinite setting that is not true. Why is that? Because we have already seen that this Markov chain is irreducible. Fine. So it has only single class, and that means that class is closed. So closed means starting from there you always remain there, but since there is only one class, so that has to be closed. So but this is an infinite class because the number of states is infinite. It is basically the set of all integers, because the simple random, for a simple random walk, the state space is the set of all integers, which is obviously an infinite set. So here this is an infinite closed class, but we have shown that this is transient. So this is an example which shows that an infinite closed class need not be recurrent, because if you look at an asymmetric simple random walk, then this whole set is a single class, the whole state space is a single class. So, it is obviously closed, but each state is transient, right. So, when you are looking at an infinite Markov chain, this recurrent implies, closed implies recurrent is not true. Another thing let me point out in this example, now you have seen this result that if you have a finite state Markov chain, then there exists at least one recurrent state, right. So, you have seen this result that if you have a finite state Markov chain, you have at least one recurrent state. But again, look at asymmetric simple random walk, this is an infinite Markov chain, and you see that all states are transient. So, again you see that something that is true for finite state Markov chain is not true for infinite state Markov chain. For a finite state Markov chain, there has to be at least one recurrent state, but if you are in a if you are looking at a Markov chain which has an infinite state space, then it is possible that all states are transient, or in other words, it does not have a single recurrent state, and an example is provided by this asymmetric simple random walk, because you have already shown that in an asymmetric simple random walk all states are transient. So, first you have just shown that 0 is transient, and since it is irreducible and transience is a class property, so all states are transient. So, an asymmetric simple random walk is transient. So, this is an example of an infinite state Markov chain where all states are transient, which does not have even a single recurrent state. So, again another result which is true for finite state Markov chain, but not for infinite state Markov chain, namely that in a finite state Markov chain there exists at least one recurrent state, but when you are in an infinite setting there may not exist even a single recurrent state. Fine, all states are transient is possible for an infinite state Markov chain, but not for a finite state Markov chain. Fine. So, this one example gives you, so serves two purposes. This is an example where you see that an infinite closed class need not be recurrent, and also you see through this example you see that an infinite state Markov chain may not have a single recurrent state. Fine. Okay. So, we will stop here today. Thank you all.